Hello students, in this video we are going to talk about negative feedback and stability of a system. We know from our previous semesters that stability is an analysis that is meant only for a negative feedback system. So I can use a stability analysis only for a negative feedback system and not for other systems like positive feedback or an open loop system, right? So with that introduction, we'll just see a general block. So here is a block diagram where there is an open loop system having a transfer function which is a of s, and to that system we have connected a feedback network beta and fed back to the input. The output of the open loop system is taken through this feedback network and then fed back to the input as a negative feedback here. And we also know that the transfer function between this input Vi and the output Vo could be returned as something like a closed loop transfer function. So I have a of s, and that is equal to Vo of s divided by Vi of s, and that in terms of open loop transfer function and the feedback factor would end up with this result, which we would have already known it. So now that I have recreated the same what I've discussed in the slide over here, so my capital A of s represents my closed loop transfer function, right? So which I normally say it as CL, so that as a kind of short form that I'll be using throughout this particular video. And here the A of s represents the open loop transfer function, and in short I will be calling it as OL, and the beta, which is going to be a purely a resistive network, which means that it doesn't have any poles or zeros in it. Yeah. So with that introduction, to talk about the stability of the system, I'm going to introduce what is known as a loop gain. So this is a term which we'll be using to study the stability of a negative feedback system. Now, to see how this particular factor, loop gain, or in short I'll try to call it as loop gain or LG, in order to see how this factor LG determines the stability, let us consider an open loop system having a single pole in it, so which is A0 divided by a single pole. Okay, and what we know is when I try to plot them in a kind of a bode plot, one for the magnitude, so which could be denoted with y scale, which is 20 log of A0, okay, and over the frequency, and the frequency is basically in terms of log scale, right? Now this omega p1 is a pole that has been created, and as we increase this input signal frequency till I reach the point where the pole exists, I'll have a constant gain, and that constant gain is basically 20 log of A0, right? And after then what happens is the gain starts decaying at a rate of minus 20 dB per decade, right? So this is what we have seen till now. And I also want to emphasize on the fact that how the phase would change whenever there is a pole in my system. So this is again the same log scale of omega, and since a pole will introduce a phase shift of minus 90 degree, I start with 0 degree, and what we know is at this particular pole I will have a phase change of 45 degree, right? And what we can approximate is when I'm at a decade before this omega p1, the phase would be almost 0 degree, and the moment I touch this particular 0.01 times that of omega p1, the phase starts getting reduced, right? And this is at omega p1. So at omega p1 we have to get a phase angle of 45 degree, and when we move further away, like away in the sense like around 10 times that of this omega p1, a decade away from this omega p1, what happens is a single pole introduces a maximum of 90 degree, and at this particular pole frequency I'll have minus 90 degree. So So this clearly states that a single pole tries to reduce the gain by a factor of minus 20 dB per decade. That is, the magnitude would be reduced by this particular factor, and also it introduces minus 90 degree, and this is the relation that we have, is creating an angle between the input and the output. Now let me come back to this loop gain expression here. So this loop gain, let me put it in the next page. The loop gain is nothing but it's a product of the open loop and the feedback factor, and this is known as loop gain. What we have assumed in the case of beta is that there won't be any phase that is introduced by this particular factor beta, right? So there is no phase change that would be added to this. So this entire loop gain, since it is a product of open loop with the feedback factor, let us try to see how it reacts at different frequencies. Okay, so now what I do is, let me try to map them. So at omega equals to 0, which means that when we apply a DC potential, and let us still assume that this open loop system has a single pole in it, which means that I can write this A of S as something like A naught divided by 1 plus S by omega P1, right? So with that discussion, we'll just see how this loop gain reacts for the magnitude and the phase changes when we change the input signal frequency. Let us have the magnitude of this. So I just write it as the magnitude here, which is again 20 log of the magnitude of loop gain, and the phase angle, which we normally write it as LG, correct? Yeah. So now when we work with frequencies that are between omega equal to 0 and less than omega P1, the loop gain will have a constant magnitude. Why? It is just because I have a constant magnitude of A naught, which won't vary between the frequencies of 0 and omega P1, and due to which what we have here is a kind of constant magnitude, and that magnitude would be equal to A naught into beta, and that's it, right? And let us look across the phase angle. So in this case, there won't be any change. Okay, so the loop gain will have a phase angle that is equal to 0 degree. Now let us see what happens when we have the input signal having a frequency that is equal to omega P1. Now in that case, what happens is the loop gain will have a 3 dB reduction, right? So in short, we can state it A naught beta, and this I supposed to write it as 20 log, right? Yeah. So this minus 3 dB, and that would be the value of magnitude that I would be having at that particular frequency, right? And what happens to the phase angle? So what we know is at this particular omega P1, I would have a phase angle that would be equal to minus 45 degree, and this phase angle is basically introduced by this open loop system, correct? So that is basically introduced by this guy, and there is nothing being introduced by nothing being introduced by the factor beta. It has all been introduced by this A of S, right? So due to which what we would get is the same 45 degree, or basically minus 45 degree. And what happens when we move beyond the frequency of omega P1? So what happens is, like, the gain starts reducing and the phase angle would starts incrementing towards the negative direction. So ultimately we will end up with something like minus 90 degree, and the phase angle or the magnitude of the loop gain will start reducing, right? And this is basically the concept that we have taken from this open loop gain discussion. Now let us see how this loop gain, or whatever the discussion that I have talked, really impacts the way that our system gets instability. Or let us see how this loop gain factor determines whether the system would be stable or not. So I'm just going to rewrite this closed loop transfer function, which could be written as open loop transfer function divided by 1 plus A of S times that of beta. Now let us assume that we are at a particular frequency. Say for example, our input signal is at a frequency of omega 1. Now at that particular frequency, I can rewrite this by letting this S a equals to j omega 1, and I can rewrite this closed loop transfer function to be as something like a of j omega 1, and even the open loop system would be operated at that particular frequency divided by 1 plus a j omega 1 times that of beta. Yeah. So now, because the open loop or basically this particular factor keeps on reducing, right? So what is happening here is, like, this is in the case of a single pole system, right? So whatever I've discussed here is all with respect to the single pole. Now let us assume that we have two or more than two poles in our system. So each of the poles will introduce, say, let us go with a three-pole system. So what we know is each of these poles will basically introduce minus 90-degree phase change between the input and the output, and due to which, if we operate at a much higher frequency, each of these poles would have already added up to 270-degree or something which is greater than minus 180-degree. Yeah. So now what would happen at that particular point? Now this entire loop gain, certainly as we operate, the entire loop gain would have reduced the magnitude. The magnitude that is introduced by this particular loop gain would have stepped down to all the way down to 1, and let us assume that at omega p1 the magnitude of my loop gain, okay, so let me put that in a proper picture, that is a j omega 1 times that of beta has stepped down to 1, and I have the angle at a of j omega 1 times that of beta to be equal to minus 180-degree. So now, how would I put them as a kind of magnitude and phase? So these two information could be clubbed as something like a of j omega 1 times that of beta times e to the power the phase angle, right? So which we normally write it as something like this, right? Yeah. So this basically becomes a quantity that is equal to 1, and then the phase angle would be 180-degree, or in short, this entire term would become a negative term, and that is what we generally mean mathematically, correct? So when this entire term goes to negative 1, what happens to the closed loop gain expression in that case? So what happens is it tends to become infinity. So under this condition, the circuit starts to amplify its own noise and starts to oscillate at a particular frequency, right? And that is said to have, or the entire closed loop system said to have unstable condition. So here I have restated this the statement that we had in the previous discussion over here, and this condition is also called as Barkhausen criteria. That's good. Yeah. So the condition which talks here, right? Now there are different ways by which we can analyze the stability of a negative feedback system. Those are something like root locus. We have different methods. One is root locus, and the other one is Nyquist plot, and the third one is bode plot. Now out of this, we'll be using the root locus method for few of the analysis, and later on we'll be emphasizing on this bode plot method to talk about the stability. Now one thing that you have to be clear is, whenever we talk about a stability, it is only the loop gain that we always talk, and neither the a of s or nor the small a of s. There is we won't be talking about closed loop transfer function, or we won't be talking about open loop transfer function. It is always the loop gain is the one quantity that we always talk when we talk about stability. So please keep it in mind. So before we start analyzing whether the system is stable or not, let us have an intuition like how I can avoid this particular situation. Now the way that I can avoid this particular situation is stated here. Now if at all, if I have the magnitude at that particular frequency omega where the phase angle is 180-degree, if I have a magnitude is less than 1, then what happens? The system will not get into unstable condition, correct? So the system would get into unstable condition if I have the loop gain, that is a times j omega, okay, this is at frequency omega 1, let us assume, okay. If I have the magnitude of this guy becoming equal to or greater than 1, and the meanwhile I also have a phase angle which is a times j omega 1 times that of beta. Since beta doesn't introduce any kind of phase, we can either neglect it. So in this case we can neglect it, or if you want you can just still add it, okay? Because this is not going to introduce anything, so which means that I have tan inverse of 0 by 0, okay? So which means that tan inverse of 0 is basically 0, and that would never add any kind of phase angle to this loop gain, okay? Now if I have these two conditions, then this kind of condition states that my system would get into unstable condition. To avoid, I have to either break any of these things, like and in this case, if I have a magnitude that is less than 1 at loop gain that is equal to minus 180 degree, right? So this is the way by which we can avoid this unstable condition. So we'll just hold this particular thing in our mind, and let us move on to the methods by which we can identify whether the system is stable, and later on we will just see how to make the system stable by using some composition. So here is a case where I have represented this closed loop system, and let us try to mimic what exactly the expression of that. So what I know is this A of S, or the closed loop transfer function, could be returned as something like a ratio between open loop transfer function divided by 1 plus the loop gain factor. So again, open loop gain times that of beta. Now if my A of S is a single order system, then I can rewrite this as something like A naught divided by 1 plus omega p1, or S divided by omega p1. So now that I'm just going to plug in this expression A of S into the open loop transfer function. So let me write it over here, that is A naught divided by 1 plus S by omega p1, and again I have a term A of S, so which could be replaced with 1 plus S by omega p1 times that of beta. Now we are going to rewrite them as something like as A naught divided by 1 plus beta times that of A naught. So this kind of expression we have already dealt, so I'm just directly writing the final expression here. Yeah, so now that let us try to see what are these factors basically. Let me choose a different color. So, yeah, so this one is nothing but our closed loop transfer function at DC, correct? So this I can write it as capital A naught, and what I have written down is nothing but the pole of my closed loop transfer function. And how would we interpret this into result? So let me put back our magnitude plot here, where I have omega in terms of log scale, and here is our dB, or I just want to plot our transfer function. Okay, so let me first try to emphasize on this small A of S, which is nothing but the open loop system. So I had in my open loop system a single pole, and that pole was at omega p1, and we also had a DC gain that is equal to this A naught. So due to which I can write I had a gain of 20 log of A naught for frequencies that is less than omega p1, and all the way I can hold till I reach to the signal frequency that is equal to my omega p1, and after then what we know is this gain would get degraded at a rate of minus 20 dB per decade. So now that we have introduced a negative feedback system with some factor of beta here, now it's obvious this value, this capital A naught, will have a value that is less than the value of A naught for frequencies that is less than omega p1, right? So due to which, if at all, if I want to overlap the plot of my A naught onto the same graph, let me choose a different color, that is I just want to plot this A naught value. So it's obvious that we will get a height that is obviously lesser than this small A naught, and due to which let us try to fix our DC gain of our closed loop system having a kind of gain that is obviously lesser than the value of this A0. So now, where exactly I would have my pole or pole of my closed loop system? It's obvious the pole could be identified as we have done here. The pole of my open loop system is read by looking at something divided by or S divided by whatever the term, right? So it's obvious in this case I have to read the same pole information by looking at the denominator of my S polynomial. When we look here, it's obvious that I have a frequency that is greater than or which is being multiplied by a factor of 1 plus the loop gain factor. So it's obvious that ultimately I would have a higher frequency, and that value could be returned as 1 plus okay, I write it as T0 here because T0 is again it's the DC parameter where I have, or in short I can write it as A of S, which is equal to A of S times that of beta. And since we are talking about DC parameter, I can just fix that by just multiplying the DC value of my open loop times that of the factor beta. That's it, right? Yeah. So it's obvious that we have increased the bandwidth at the cost of reduction in the closed loop gain. And this is what happens here. What we have seen till now is with respect to the bode plot, and that too with our magnitude plot here. Now what happens, how do we visualize the things in a root locus? What we know is I had a pole in the left half of the S plane, and this is my S plane. So I have j omega and sigma towards the x scale, and this is my S plane, and I had a pole somewhere here, and that pole is at omega p1. And now as we put a negative feedback, what happens is, depending on the factor of beta, this this is the value of pole that we had when beta equal to 0, which means that we talk about open loop system and when there is no feedback in the system here, right? So having this beta equal to 0, which means that there is no connection between the input and the output. So we don't have any connection. So whatever the signal I have fed here would be outputted through only through this open loop system, right? Yeah. So now what happens when we try to increase the value of beta? Now that creates a kind of feedback through this, and in this case, which you would have already studied, as we increase the value of beta, the pole tends to move towards the left side, right? So, and at a particular value of beta, let us assume our pole has got shifted right from here over here, and this frequency is given as omega p1 times that of 1 plus T0. So the same kind of graph I'm just going to show in the next, like in this particular slide here, right? So the first plot that I have plotted here is all the open loop transfer function, and we had that open loop transfer function having a pole at omega p1, and when we put a kind of negative feedback system, it's obvious that we get a gain that would be smaller than the gain of our open loop system, and that is recreated with this kind of graph. So what we have done is we have overlapped both our open loop as well as the closed loop transfer function onto the same graph here, and in turn we can just directly read what happens to our pole frequencies. The pole has got shifted to a much higher frequency in the case of a closed loop system, and that we can visualize in the other way by having this value of beta that is equal to 0, or having T0 that is equal to 0. And what happens when we had a finite amount of T0, that would actually move our pole to a much higher frequency. Okay, so in short, what I can state is the bandwidth of the system has got increased by a factor of 1 plus T0. I think the color is not clear. Okay, and the gain, and what we compensated over the other end is the closed loop system gain has got reduced by the same factor of 1 plus T0. Okay, so these are at DCs. So now let us move on to the next one. Okay, so here is an exercise what we have asked here is that consider that there are two poles in a system, and discuss about the stability of the system. So I'm just going to use our root locus method to talk about the stability of the system. And let us assume that we had two poles. One is omega p2, okay, which is at much higher frequency, and we also had one more pole which is at omega p1. So there are two poles in a system, or in short, I can write this open loop had two poles by 1 plus s by omega p1, and it also had a second pole at omega p2, and this is what we have, right? Yeah. So now we'll just put this particular open loop system into a negative feedback system with some factor of beta. Okay, so these are the pole locations which when beta equal to 0, or when there is no feedback in our system. Now what happens when we try to increase the value of the factor beta? Yeah, so before we talk about it, what is the maximum value of beta that we can have in a system? Yeah, so it would be equal to 1. So beta will generally have a value that ranges from 0 to 1 to a maximum value of 1 here, right? Yeah. So with that in mind, let us try to increase the value of this factor beta. Now what happens in that case? To talk further, I also need to write this a of s, that is our closed loop transfer function, which again could be written as something like beta times that of a of s. And when I'm just going to plug in this entire expression onto this expression, so which would be given as a of s equal to a naught divided by 1 plus s by, so I have done some simplification which is in general directly readable. Okay. So beta times that of a naught. Yeah, so this is the expression, but the general question here is like, what happens, or how these poles would wander around this s-spline when we talk about, or when we try to increase the value of beta. I guess you would have already known, like the pole omega p2 would tend to move towards the right side, and the omega p1 would tend to move towards the left side, right? So at a particular frequency, or at a particular value of beta, what happens is the pole both would meet each other at a particular value of beta. And let us assume that the value of beta when both the poles meet each other is assumed to be beta 1. And what happens if we further increase the value of beta factor beyond this beta 1? It's obvious that one of the pole would try to move up, and the second pole or the other pole would move towards the negative end, making the pole to be a complex conjugate. Okay, so as we increase the value of beta, it moves something like this, and this is what you would have already learned in your control systems, like how the pole would move when you increase the value of beta or some gain factor or something, right? Yeah, so let us assume that this is the movement that we had here. Yeah. Now let us see, or let us try to discuss whether the system is stable or not, having a particular value of beta. Now what we know is, like, the further the increase in the value of beta, the poles will always stick inside the left half of the s-plane. That is, the poles will try to move up and down, right? All of these, sorry for the technical interruption. Yeah, so the pole will generally move up, and the other pole will generally move towards down. Now in either cases, what happens is the poles generally try to tend to stay inside this left half of the s-plane, which means that the system will be always stable irrespective of whatever the value of beta here. But as an exercise, we'll try to identify what is the value of beta at which both the pole intersect each other. It's a part of the exercise that is given or discussed in our textbook. So let us try to do that. Now let us try to find the value of beta 1 at which we have both the poles intersecting each other. Now to do, I'm just going to further simplify this expression, which is a naught. So these are just simple algebra, so I just rewrite over here, which you can do it by yourself. There is no need of any further explanation here. Yeah, so this is what we have, and I have a second order polynomial in my denominator. And what we know is like the root of this characteristic equation d of s, or basically the what I really mean is this is my d of s, and the characteristic polynomial or the roots of this d of s could be identified by the well-known method, so which is taking minus b plus or minus square root of b minus 4ac times that of 2a. So I'm just going to adopt the same thing, and the only thing that we have to encounter is like what are the values of a, b and c, and I guess all you people might be knowing it. And this is the value that I have for the value of b, and this is the value that I have for the value of c, and the term over here is just 1, and that 1 is equated to a here. So when we plug in all of these quantities to the expression, that helps us to identify the roots of this particular polynomial. So plugging in all of these values would end up with a term something like this, right? The roots of the polynomial. Right. Yeah. So now how would we identify this beta 1 by looking at this roots? Now what we know is like this particular term, the term that are under the square root, okay, and this is a region where I have poles still having real term in it, right? And at that, and the moment I go beyond this beta 1, the poles becomes complex conjugate. And what would be the value of this second term, that is let me put it in a marker here. Yeah. So what happens to this particular term that I have under the square root when we had poles exactly matching one over the other, or exactly overlapping one over the other? So this is basically equal to 0, right? Yeah, since because this particular term would end up having a kind of imaginary term beyond the value of beta 1. This is supposed to be equal to 0, and for value of beta that is less than beta 1, this would be a positive, and for any value that is any value of beta that is greater than beta 1, that this entire term would go to a negative value, correct? So we are at somewhere in between the positive and the negative value of beta, and that is supposed to be equal to 0 when we have poles overlapping one over the other. And due to which, when I'm just going to write this omega p1 minus omega p2 square supposed to be equal to, or I'm just trying to shift the terms, supposed to be equal to the factor that we had in the other end of our expression, and we have a value of beta that is equal to beta 1. So doing a simple math, we would end up with having a beta value that is equal to, I'm just writing the result directly, so you please better go through do the arithmetic behind this to exactly know how we get this final expression here. And this is the value of beta 1 that we need to have when we want to have a critically damped response, right? Yeah, so we are going to derive some of the results that we have done, right? So I've just given some comments. What we have seen here is when we have a system or a closed loop system having either one single pole or two poles in it, the system is always stable because the poles tends to stay inside the left half of the S-spline, and due to which the system is always said to be a stable system, correct? And also, like there is no way by which like it's always looking back into our S-spline and then see for what particular value of beta I have the system being stable or not, right? We need some set of parameters to define whether the system is stable or not by looking at a particular predefined value. In general, we have some set of parameters to check whether the system is totally stable or marginally stable, or the system is unstable. So we'll talk about what are those parameters, and basically those parameters have to be extracted from the loop gain, as I said before. Okay, let me see what are those. So now that I've taken a system where I have 3 poles in the system, and I'm looking across my same root locus and try to see how the poles would move and how or what particular value of beta we would end up having a negative feedback system entering into an unstable condition. So all the discussion that I'm making here is all with respect to root-locus method, but after then we'll also talk with respect to the bode plot. So these are the open loop system transfer function. So what I've written here is the open loop transfer function, and I have those poles at these locations, okay, and the pole that we have as the most dominant pole is our omega p1, correct? And these are the positions that we have when beta equals to 0, that is when there is no closed loop system. Now what happens when we try to increase the value of beta factor? Now that is moving towards the value of 1, okay, yeah. So from our previous discussion, what happens is the pole that we had at the left half of the plane, the most left one, right, the omega p3, so will tend to move towards its left side. But what happens to this p1 and p2 poles? It's obvious that these two poles will try to move towards each other, and at a particular point they would try to have a kind of interaction, okay. Both the poles will end up lying at the same frequency. And what happens after as we increase the value of beta factor here? It's obvious that these poles will try to make a route which is something like a kind of over the circle or over a semicircle, right? Just because, so they generally break away at this particular frequency at an angle that is basically 180 yeah. So at an angle which is basically 180 degree divided by the number of poles in the system, so which is basically 60 degree. So they will break away at that particular 60 degree angle, and they try to move towards the zeros. Since this particular transfer function doesn't have any zero, we have zeros at infinity, so they try to tend to travel, right? And we end up entering into the right half of the S-plane. So now we have poles. So whenever we have poles either at imaginary axis or in the left half of the S-plane, what we know is the system becomes unstable. So the system becomes unstable, right? Yeah. So for a particular value of beta, we get into this particular region, right? Now, and that region we state it as an unstable region whenever we get into right half of the S-plane. So all that we know it. So it's just a kind of revision that we make here, right? Yeah. So now let us see what happens. Let us try to have a kind of mimic across our the bode plot method. So this is a kind of representation that we have done. Okay, we have the poles at omega p1, omega p2, and omega p3, and across each of these poles there is a kind of decay in the gain expression. So either we can write it in terms of minus 6 dB per octave, or it can also be stated as something like minus 20 dB per decade. So either of both is a valid one, okay. And when we encounter a second pole, the rate at which the gain reduces would be minus 40 dB per decade, or in other words it is minus 12 dB per octave. And when we encounter the third pole, the gain or the magnitude of the open loop system would start decaying at a rate of minus 60 dB per decade. So all of these informations we note, and just a kind of plot that we have done, right? And also what we know is the phase angle, right? Yeah. So the phase angle at omega p1, when we encounter the first pole, the phase angle would be equal to minus 45 degree. Now, how do we evaluate the phase angle? So probably I'll just write an expression and show you like how exactly this is supposed to be calculated. So the phase could be written as phi, and that is since because all of the poles that we have, or all we have is just the poles, it would be real divided by the pole location, right? So I need to have 3 such components, omega divided by omega p2, this is due to the second pole, and the phase due to our third pole, which is given by this omega p3. Sorry, it's not that clear. That's supposed to be omega p3 here. Okay, yeah. So now, whenever we have a frequency, that is the input frequency, that is less than this omega p1, so say for example over here, now what happens when we plug in these values? So the ratio that we would get out of this would be less than a value of 1. Or let us assume that we have 0 for this particular ratio, that is for omega that is less than omega p1. It's obvious this term would, or this ratio would be closer to the value of something like equal to 0.1 or something, and over here it would be something like 0.001 and 0.0001. Okay, so it's all the assumptions that I'm making here. Okay, yeah. So now when we try to compute what is the phase introduced by each of these components, when we add up, so this would basically create a kind of angle that is closer to the value, approximated to a value of 0 degree. So each of these components would introduce a 0 degree at a frequency that is much lesser than the value of omega p1. And what we know is when we increase the value of this input signal frequency, and when this frequency is exactly at omega p1, the first term will have a ratio that is equal to 1 in this case, and due to which what we know is tan inverse of 1 would be equal to minus 45 degree. And but at this particular frequency, we have when we compare our omega with omega p2, this ratio that we have out of this particular term would be still lesser than the value of 1, and that we can approximate it to 0, and tan inverse of 0, we know it is equal to 0 degree 8, right? And so the same kind of analysis could be applied even for the third pole, because we have omega p3 that is much larger than compared to the frequency right now at where we are, right? So this also turned out to be a 0 degree. So the total phase angle would be 45 degree at omega equals to omega p1, and that is the one that we have plotted here. And with similar discussion, let us move on to a higher frequency. So let me have some space here. So right now, when our input signal frequency is equal to omega p2, so now what would happen right now? This particular factor, or this particular ratio, that is omega divided by omega p1, would be obviously has a value that is greater than 1. Okay, let us assume that this value is so large that is almost closer to the value of 100 or more than that, right? So what happens to this tan inverse of 100 or 1000? So this turns out to be 90 degree, right? That could be approximated as infinity, and when we approximate that, we already have attained the maximum phase shift due to this omega p1. But what happens to this ratio here? So I have omega that is equal to omega p2, so omega p2 divided by omega p2 would be 1, and that introduces a 45 degree phase angle. And when we compare this omega p2 or omega with omega p3, the ratio that we attain over here would be far small, like say for example like 0.01 or 0.001 or something, right? So this will not introduce any kind of phase angle, so that creates just something like 0 degree. So the total phase angle at frequency that is equal to omega p2 would be equal to minus 135 degree, and that is the one that we have marked here. At omega p2 we have 135 degree. So let me just take the second or the final pole, okay, and let us see what happens in that particular case. So let me choose a different color here, omega p3. Yeah, so now in this particular frequency, it's obvious that this ratio that we have here would be obviously much greater than the value of 1. Okay, so we have the quantity that is greater than 1, and that ultimately introduces minus 90 degree. And here again what we have is, I have omega p3 which is much larger than the value of omega p2, so this again the ratio would be much greater than the value of 1, and due to which that also introduces minus 90 degree. But what happens to this third factor here? We have a ratio that is equal to 1, and due to which the tan inverse of 1 would lead to 45 degree. So the phase value at this particular frequency would be equal to minus 225 degree, and that is the one that we have marked over here, right? So at this omega p3, I have a phase that is equal to minus 125 degree. Now what happens when we move our input signal frequency beyond omega p3? It's obvious that this ratio will also become a value that is greater than, or much greater than the value of 1, and that we can approximate by having or this particular pole trying to add a 90-degree phase angle to the term, and the maximum phase that we would end up at much higher frequency would be equal to 270 degree. Hope that whatever the discussion that we have talked till now is all about the open loop system. Now, how do we check the stability of our system right now? So, as I've stated before, we need to have a negative feedback when we talk about stability of the system. Okay, so let us assume that we have a negative feedback with a feedback factor that is equal to beta 1. So I just go with a beta 1 factor, correct? Now, and let us assume that this value is certainly higher than the value of 0, but not exactly equal to 1 or something, right? So let us assume that I have some value of beta, and that value of beta is slightly greater than the value of 0. Okay, and according to this, when we put this particular value into our closed loop transfer function, which is, this is again a of s divided by 1 plus a of s divided by beta, right? And when we extract for the signal frequency that is less than omega p1, then we can approximate this to be a naught, and that is equal to a naught divided by 1 plus a naught times that of beta. Now, this quantity is basically small just because the value of beta factor is small. Now, due to which the value of a naught that we would get is certainly closer to the value of this small a naught, that is our open loop DC gain. So with that in discussion, let us assume that I have certainly a small closed loop DC gain that is somewhere over here, right? And let me label this, and this value is equal to 20 log of this capital A naught. Now, if the value of this guy or this A naught, okay, if this value is so large, or the DC gain of the open loop system is so large, now what happens to this entire term that we have here? It's obvious this is going to have a value that is much greater than the value of 1, and due to which when we compare this a naught times that of beta with respect to the 1, what we can do is we can approximate that to have, or we can approximate, or we can neglect this value 1 over here, and that would lead to a kind of gain that we would have when we have a frequency that is less than omega p1, and we can approximate that to have a gain that is equal to 1 upon beta 1, which we have already from the previous semesters we would have already known it. Okay, and due to which I can just write it as something like 20 log of 10. Right now the value of a naught I can approximate to just 1 upon beta 1. Yeah. And this is the closed loop transfer function, and the moment I reach here, certainly the what would happen when we try to intersect at this particular junction, right? What happens whether the gain will stay as it is, or we have to tend to bend and try to have some degradation in our result. What could happen? Let us pause for some time. Now it's obvious that this a naught at this particular frequency, that is somewhere closer to omega p2, is not same as we had it over here, right? So we have certainly lost some amount of a naught, or the open loop gain at this point is higher than the open loop gain that we had here, which means that at this particular point, or at this particular frequency, I have a value of open loop transfer function gain that is smaller than compared to the same gain that we had just before. True. Now, due to which, now at that particular frequency, what happens is this particular term, that is a naught times that of beta here, sorry if it is not visible, I'll just put, yeah, so this particular value becomes almost comparable to the value of 1. Okay, so what I can state is this could be approximate to have a value that is right now lesser than the value of that is quite smaller than the value of 1. And now for frequencies omega, that is under this condition, for frequencies that is greater than omega p1, I can approximate this in or the closed loop transfer function to have a value that is a naught divided by or a of s, because we don't have a naught at that particular frequency, which is smaller. Okay, so I just write it as a of s instead of a naught, right? So this value right now becomes comparable to the value of 1, and if we assume that this value is smaller than the value of 1, then we can approximate this to have something like a of s. Now what we exactly mean by this for frequencies, or somewhere here, right, somewhere here where I have a frequency, input signal frequency that is greater than omega p1, what would happen is this quantity becomes much smaller than the value of 1, and due to which beyond this particular frequency, both the closed loop and the open loop would follow the same kind of graph. Okay, so this is the graph that we would normally have for a closed loop transfer function. Clear? I hope this information is clear to you, and so with that I'll start further discussion of how these poles are exactly moving. Yeah. Now what we really wanted to analyze the stability, is it the open loop discussion or the closed loop discussion? Neither, right? Yeah. So if I want to analyze any stability or a kind of stability of a system, what we really wanted is the loop gain. It's neither the open loop transfer function nor the closed loop transfer function, right? Yeah. So how I can extract the information? So what we know is, let me just try to have. So what we know is the loop gain is given by a factor which is 20 log 10 of a of s times z of beta, and this is the magnitude, right? So I just want to write the magnitude here, and let us see how this is going to this could be returned, right? So now what I can do is, since it's a kind of product that we have, and since this product is coming under this logarithmic scale, we can split them as a kind of addition of two things, right? So which is a of s plus 20 log 10, sorry, it's 10, the base is 10 here, to the factor of beta here. True. Now again, this could be returned as a of s minus 20 log of 10 with 1 upon beta here. Now what is this information that I have done here? This is a kind of gain that we have for an open loop system, correct? So this is a factor that comes from the open loop transfer function. And what is this factor? This is a factor that comes from basically from the closed loop. Now when I try to subtract these two quantities, what I would end up is a kind of term that is equal to the loop gain. So let me just switch back to our slide and then talk about it. Yeah. So now whatever the region that we have between this open loop and the closed loop is normally tend to be called as the magnitude plot of our loop gain. True. So all of these things we have done just by subtracting those two regions. So now let me try to clear up some space here just to have further discussion. Yes. Okay. So now before I really talk about the magnitude of our loop gain, let us think for a while, like what is the amount of change that we are, how do we extract the phase of the phase angle of our loop gain? What we know is the loop gain is nothing but, or the phase value could be extracted as something like a of s times z of beta, and what we know is this beta doesn't introduce any kind of phase shift, right? So anything that we read for a of s would be the same as that of a times that of beta, right? So both these phase values would be same. So I can retain this same graph whenever we talk about the phase angle of a loop gain, but the graph of our the graph with respect to the magnitude plot of the loop gain is pretty different. So right now what I'm going to do is I'm just going to plot the loop gain magnitude plot. So in this case I'm talking about something like 20 log logarithmic with base of 10 and then a of s times that of beta. So this is a graph with y scale having loop gain as its magnitude. Okay? And again we have this omega as the x scale with logarithmic scale here, right? Yeah. So now in this, so this entire information has to be plotted, like whatever that has been shaded here has to be plotted over here, right? So let me assume that this is the same height, so probably not exactly 1-to-1, it's a kind of scaled up version here. So this exact information is being plotted here, and that this value is right now equal to 20 log 10 because I've subtracted both these values, and that is equal to 20 log of a naught times that of beta. Okay, and there is a kind of pole, and that pole is exactly at omega p1, so I just mark this omega p1 here, and at that particular frequency what is happening to the graph is start getting degraded at a rate of minus 20 dB per decade, right? And we intersect or the loop gain becomes 0 dB at omega p2 here, right? So and after then the graph would try to have a further decay, right? So this is decaying at a rate of minus 20 dB per decade, and whereas here, so probably not the best way of my drawing here. Yeah, so what happens is there will be a further decay, and that is equal to minus 40 dB, but doesn't matter. Okay, so anything after this I will have omega p3 here, and the only thing is instead of having the baseline here, the baseline right now falls at this particular juncture where I had my closed loop DC gain, right? So this entire plot has to be shifted over here when we talk about this. Okay, and this is how the graph would further gets down, and once I meet this omega p3 there will be further decay of minus 60 dB, the same kind of things. Okay, so this entire graph has to get shifted to this kind of baseline, that's it, right? And this is nothing but our magnitude of our loop gain, right? Now how would we plot our phase? The phase is pretty simple, so the same kind of graph. So what I can do is I can just again draw this with respect to the omega log scale, and then I have the phase angle, and whenever we have we are at a frequency omega p1, what I know is there will be minus 45 degree, and then when we have this omega p2, that is exactly here, okay, sorry, omega p2 will have a phase value that is equal to minus 35 degree, right? And this is how we would end up. And further, when we encounter the third pole, we'll have this minus 25 degrees. So there is no change with respect to the phase when we try to plot for loop gain, correct? Yeah. So now that I have given enough information, like how the system or how to plot the loop gain from a bode plot, but how do we analyze whether the system is stable or not just by looking at this sort of graph? So in order to talk further, or in order to talk about the stability of the system, we have to introduce two further terms. They are known as phase margin and gain margin. Okay, since my video is going out of time, like more than an hour, I'll just hold and put it in a second part of the video, the further discussion. Thank you.